Okay. I will share my screen. I hope you can see it. Okay.
Yes, we're seeing it currently. Thank you.
Okay, so thank you for the presentation and good afternoon, everyone. So let me start introducing Sub2Code project. In this project, we are 13 partners coordinated by Sintef, and it has a duration of 3 years that will finalize this December. So the goal of Sur2Code is to enable the use and uptake of aluminum in new sectors involving products with complex shapes by new sustainable manufacturing methods and surface treatments. So at CDTech, we have selected anaphoretic deposition as the sustainable surface treatment. Why? Because it is suitable for coating complex shapes. It is an efficient and scalable process, and it is also ideal for mass production. And we are applying this anaphoretic deposition process in 2 use cases: in electric engine housings of the food and beverage industry, and also in accessory gearbox of the aeronautical industry. So very briefly, anaphoretic deposition implies the electrophoretic deposition of negatively charged particles into the surface of the part that needs to be coated, which is the anode, by applying an anodic current. So after this electrophoretic deposition process, we need a thermal treatment to enhance the coating adhesion and durability. Because this thermal treatment promotes the cross-linking of the polymer. So moving now to the first use case that I want to explain you today, which is the electrical engine housing. Our objective with this use case was to replace stainless steel by aluminum with an e-coating to withstand the harsh operating conditions that are used in the food and beverage industry. So in this table, you can see the requirements that we need to fulfill with this use case, such as thermal conductivity, adhesion, thickness, roughness, and corrosion and chemical resistance. So we apply the anaphoretic deposition process to this 6082 aluminum alloy. We characterize the properties of these requirements, and we fulfill most of them, but not the requirement about chemical resistance. So our challenge here in Sur2Code and in this use case was to increase the chemical resistance of the coating to aggressive cleaning agents used in the food and beverage industry. So we need to pass the Ecolab test. This Ecolab test involves immersing the part to be tested during 28 days in 5 different cleaning agents. Some of these cleaning agents were acid and 2 of them were alkaline. So what we found was that, the e-coating survived in the acidic cleaning agents for the 28 days. But when we immerse the e-coating in the alkaline ones, from the first day, we observed degradation of the e-coating. So we have been working on finding on different strategies to try to increase this resistance to alkaline products. For example, by modifying the e-coating curing temperature, or by analyzing different pre-treatment steps before the e-coating. Like, for example, applying an anodizing coating before the e-coating. So here is the summary of some of the strategies we have used. So we have cured the e-coating at 120 degrees, which is the standard procedure that we usually use. We have also cured it at higher temperature at 180 degrees. And we have applied a thin anodizing layer. In this case, it was tartaric sulfuric acid anodizing before the e-coating cured at these 2 temperatures. So what we found was that this e-coating system the one that implies anodizing and e-coating at 180 degrees, was able to survive during 28 days in this alkaline cleaning agent. Why? Because we have increased a lot the barrier properties of this coating system. What we found was that the curing temperature governs the e-coating cross-linking, and thus it's resistant to alkaline products and also to corrosion, and that the previous anodizing layer improved the alkaline resistance because it prevents blistering and it prevents the swelling of the e-coating. And we have also found that when we have applied anodizing layers with different thicknesses, and an anodizing layer of 2 microns was enough to prevent the swelling of the e-coat. So this process can be scaled up in pilot plants, but for that we need a special tank, which is this one you can see here. This tank consists on the electrocoat tank and also a permeate tank and ultrafiltration system. Okay, so moving now to the second use case that I want to explain you today. It is a gearbox, accessory gearbox that is used in the aeronautical industry. And in this case, our challenge was to apply the coating selectively on some areas of this use case that have been previously repaired by cold spray, by another partner of Sur2Coat project. Okay, so as I have explained before, the coating process is usually applied by immersion. But now we want to apply it selectively, just where we need it. So for that, we have been working in these last steps of the e-coating process, anodizing, rinsing, e-coating, and curing. So in order to apply the curing step selectively, instead of putting the part in an oven, which is usually done, we are working on curing the coating by infrared light. And in order to apply the anodizing and the coating process selectively, we are using the brass plating technology. So the brass plating technology implies recirculating the electrolyte through a tool where the counter electrode is placed. Okay, in this case is the cathode. We move this tool towards the surface that we want to treat, where we want to apply the coating, and at the end we have there the coating. So we have been working in Sur2Coat in modifying the coating formulation to enable the infrared curing. We have designed the racks and the connections. We have optimized the electrical parameters of the coating process and also the cleaning steps between anodizing and e-coating that we found was really needed. Okay, and the next days we are going to apply this selective process that we have developed in small pieces in the demonstrator of the project in the areas that have been repaired by cold spray. Okay, so the main message that I want to tell you today is that the e-coating process can be optimized by modifying the formulation or also by optimizing process parameters to have coatings with high corrosion and chemical resistance. And that this process can be applied by immersion to treat the whole areas of a part and also selectively by using the brass plating technology. So thank you all for your attention.
Thank you, Belén. Just on time. There is one question for you from Jim. I think I said it correctly. It says, does the overall e-coating method process speed up the standard method to achieve relevant results? If yes, what is the time scale of improvement? You have it in the chat if you want to read it. Maybe it's easy.
Okay, so we will stop sharing.
The question is regarding the time. maybe the speed up or...
Okay, does the overall coating method process speed up the standard method to achieve? Okay, if we are talking about the first use case that I have talked about, this use case is currently produced by stainless steel, so it is not, so the standard process has not got any coating, okay? But this is a quite rapid process because the coating process usually needs only from 1 to 3 minutes. And then we need the curing step that could be done between 60 and 20 minutes. So it's not a long process, okay? And it's quite easy to produce. Okay, the time to a scale of improvement. I don't understand the last question.
I think it is regarding if there is a speed up in the process. What is this time of the speed? I think, or maybe if minutes or hours.
Yes, like in total it could be 1 hour or a little more because you need all the pretreatment steps. But what is the coating process is some minutes. Yeah. I hope I have answered the question.
I think so. And if there is more question, maybe at the end of the session, you will say it. Okay, thank you so much, Belén. We'll continue with the program. Now is the time of Francisco Gontat of the project Fabulous, which the presentation is going to be about the advancements in 3D meta surfaces, revolutionizing optical sensor. And the case study will be the development and implementation of high resolution 3D meta surfaces in optical sensor, enhancing precision and reducing device size for advanced industrial application. So
thank you very much.
The floor is yours.
Thank you very much for the presentation. Okay, so today I'm going to speak a little bit about the Fabulous project and the objectives and the main use cases that we are developing in this project. The Fabulous, as has been said, is a project devoted to the fabrication of 3D metasurfaces that can enable the generation of high efficiency new optical products. So the goal of the project is developing a manufacturing platform that will allow us to produce these metasurfaces with a high throughput, high resolution, and fabricate them at a larger scale. So the platform should be able to fabricate these metasurfaces in a 3D tailored way to produce these structures on top of both planar and non-planar surfaces, and as well keep high efficiency and extremely high precision. The partners that are involved in this project are IMEC, which is my institution, Heidelberg Instruments, which is one of our technical developers, as well as IMT Atlantic, and fourth, the Institute for Research and Technology from Hellas, from Greece, Fraunhofer IISB, who collaborates with us in the co-optimization of the manufacturing processes. Thales, Ficosa, and Stellantis are the three end users that are collaborating in the Fabulous project, developing these use cases. PlanOpSim help us with the simulation of the structures, with the definition of the structure that are designed for the metasurfaces, together with Forth. And Modus helps with the dissemination communication activities, while Iris is in charge of the life cycle analysis of all the developments that are carried out in the project. So in Fabulous, as I mentioned, we are developing a full methodology. So the idea is to tackle the problem from an overall point of view. So we are designing the metastructures, starting from the meta-atom design, the meta-atom distribution, meaning not only the sizes and shapes of the meta-atoms, but how they are distributed on top of the surface. And then working on the manufacturing from a simulation point of view, simulation of the process, to enhance how we use light to enhance both the productivity and the resolution of the metal surfaces that we are fabricating, with the final goal of fabricating 3D metal surfaces that could be demonstrated in these 3 use cases. As I mentioned, we have 3 different use cases. The first of them is based on the manufacturing of high-efficiency solar cells for high-altitude platforms. The idea in this use case is to fabricate metal surfaces that can enhance the way that light is used in these solar cells. So in this way, if we fabricate more efficient solar cells, we can reduce the amount of time that these high-altitude platforms that are used for broadband communications has to download from this high altitude to be refueled. So enhancing the efficiency, we can reduce the amount of fuel that is used for these high altitude platforms. In the case of the automotive sector, we have 2 use cases. One which is related to the fabrication of sensors and cameras for cars, which are more efficient, so we can use light in a more efficient way, and using at the same time a lower weight of the optics that are necessary for these applications. But we can also tailor the way we use light, not only for sensing application, but also for lighting applications. And the third use case is based on this approximation. We are defining and fabricating metal surfaces that allow the cars to illuminate the road in a better way. So these metal surfaces will be applied on the running lights of selected car model, which are the lights that are now used in the cars that are switched on for the whole day once the car is switched on. But not only we have these 3, let's say, use cases, we have a fourth, let's call it a fourth use case, which is the development of the technology for the fabrication of the metal surfaces, coming from the experimental setups that are developed within the frame of the project and that were developed in previous projects where the core technological partners of Fabulous were involved, making use of advanced diffractive optics like diffractive optical elements or spatial light modulators, enhancing the projection that we are using with these machines, and put these experimental developments into industrial machines, like the one that you can observe here, which is the one from Nanosky, which is going to be one of the associated partners of the Fabulous project in the next year, helping us with the development of some of the use cases that I have presented early on. So, as I mentioned, we work on the design and on the manufacturing. So in order to design the structure, we have to define which is the metal atom that we are using for the fabrication of the metal surface. And the easiest way to fabricate it is to have a small design and design this structure based on propagation, on accumulating phase propagation, via the propagation, on a small light wave. So once we know how the phase changes in each of these small structures, we can create a lookup table with a full range of these metal atoms. And by changing the distribution of these metal atoms with different heights and sizes, we can tailor the way the lights interact with these metal surfaces, providing the beam steering or beam focusing in a very simple way. So once we have defined how the metal atoms are designed and structured along the surface, we have to work as well on the manufacturing of these metal atoms. And the idea is to do it in a parallel way. Instead of going to the fabrication one element by one, to use advanced parallelization techniques like the use of spatial light modulators to tackle the fabrication of several metal atoms at the same time. Like, for example, these scanning electron microscope images, here we are projecting 16 spots all at the same time. And by changing the processing parameters, we can observe how we can produce these small cylinders with different diameters. changing the diameter, controlling the diameters, and but not only the diameter, but also the way they are distributed on the surface. And you can observe on the bottom image of the on the slide, we can define different arrangements that will produce different effects. Like, for example, focusing, like, for example, light bending, but also additional functional surface properties like the reduce wettability, change in the transparency of the material and enhance transparency without affecting the optical image that we are observing. For example, when we are using this kind of structures for the combination with CCD cameras. We can fabricate not only small cylinders, as in the previous example, but we can fabricate different shapes. In Fabulous project, we have observed that the definition of different meta-atoms, like small cylinders, like thick small wheel guides, or square areas, or annular structures, can lead to a different light interaction, different changes on the propagation of the light. So by adjusting the shape and the structure, we can fabricate different optical functionalities. And this approach, when used with the spatial light modulators, it's really very precise, but not only precise, it's very reliable. We can fabricate these kind of structures on large areas with a very good repeatability, as we can observe here in this scanning electron microscope images on the right side, where we have been able to project at the same time each of the annular structures, each of the square structures with different sizes, and the cylindrical structures with an average of 5 spots, one close to each other, with a similar size along the whole surface of the structure. So this means that with this approach, we can fabricate the metasurfaces with a higher throughput, with a very good resolution, with a very good repeatability, which is a very nice result for the industrialization of this technique. So, as a final remark, the message I wanted to give you is the fact that we are developing a complete fabrication platform, coming from the design point of view, developing simulation and optimization tools that help us develop the manufacturing process. And those strategies, together with the parallelization techniques, allows us to produce, as we observe, very good resolutions and very high throughputs for the fabrication of the metasurfaces. They will be industrially available. They will be integrated in standard machines, and those structures, this approach of the design with the tools for designing, parallelization, optimization, can be applicable for highly demanding optical application, like the case of sensing, lighting, or even the photovoltaics industry. And that's everything from my side. Thank you very much.
Thank you, Francisco. Thank you. We have a question in the chat. They're asking, when you manufacture the metals, do you provide QC, QA? If yes, what is overall successful rate of fabrication in the production?
We are not fabricating with metals. That's probably something that I didn't mention, but we are working with polymers, transparent materials, because we want to fabricate. In this case, we want to fabricate metal surfaces that are suitable for transparent applications. In the case of metals, they are most for antennas or other kind of or reflective devices. In our case, all the use cases are based on transparent materials. So since the transparency is very important for us, we are using polymer hybrid resins that once cured has the form refractive optics similar to glass and similar properties as well to glass.
Okay, thank you. At the end, we have more time for questions. Thank you, Francisco. Now it's my pleasure to introduce our next speaker, Miguel Gomez from FAID. He will be presenting the project Vilasurf. This project studies the application of bio-inspired riblets via laser functionalization on hydroelectric turbine surface and industrial fans, achieving significant reduction in flow resistance and improved energy efficiency. Miquel, the floor is yours. Whenever you want, you can share your presentation. Thank you.
Thank you very much. Do you see the presentation?
Yes.
Okay, thank you. Well, with the time I have, I'm going to give a few headlines of the project, okay? So the main goal of Vilasurf is to develop and integrate a process of high throughput to functionalize complex 3D surfaces with tailored design riblets, bio-based riblets, to reduce friction and improve the environmental footprint. So from one side, we have to design the riblets, and from the other side, we have to design the tools with which we want to do this, both laser technologies and monitoring. Okay. So these are the partners. Okay. We are the coordinators and technology developers, together with Aymen, Fraunhofer IBU, Fusion Bionic, and Supergrid, and Workshop of Photonics from Lithuania. CLAB and Global Hydro are the users. Bionic Surface Technologies is also doing the development of the riblets. And finally, SECFO is doing the simulation and communication. So in what sectors have we focused? Mainly in two. The first one is the hydro turbines, because according to previous results with riblets, we expect an increase in efficiency between 2 and 5%. This means that having an installed capability of 200 megawatts in this case of Global Hydro, we could generate 50 megawatts hour at no additional cost. In the case of the second demonstrator, that is the HVAC, in this case in industrial fans, CLAB sells a capacity of 200 megawatts per year. So if we can increase efficiency in 2%, we could save 4 megawatts of power. And we know that the energy is more and more important factor these days. Also, the idea is to reduce the sound, because these fans are normally installed nearby populated areas, so it's more attractive, for example, to use it in heat pumps to increase the market share. The other focus, or the other area in which we have focused, is to try to preview in what other sectors could we expand this technology. So that's why we have focused in 3 different laser technologies, not only to focus in these two sectors, but also to expand this technology once the project has ended. Okay. So this is the manufacturing path. Basically, you have to define the demonstrators, what are the needs, then define the surface visualization. And in this case, our work has been more or less using 2 work packages in parallel. In the first one, we do the simulation, we develop the 3D laser technologies and do a pre-validation, because you have to make sure of what type of riblets can you reproduce and that they have the effect that you need. And parallelly, we have developed an inline monitoring module, a multi-axis positioning module, laser texturing module, and we have integrated everything in a prototype. The texturing validation and characterization is something in which we are working right now at the moment, because the project is ending in May 2026. So the 3 laser technologies we have been working with, one is the LIP, that direct laser interference patterning, that, as most of you know, in case you want to use or to obtain a 1D pattern, you have to use 2 beams, and the period is determined by the angle between the beams. So, of course, depending on which period you are targeting, you can obtain one period or the other. In this case, we have focused in periods lower than 50 microns. In the case of the laser writing, that as you most of you know, it allows you to reproduce any free form. We have been focused in periods higher than 50 microns. We know that changing the spot size, you can focus on different periods, but this was to complement the direct laser, the DLIP, sorry. And the third one, the microcladding, has been focused in much higher periods because it has a high throughput. So in the future, in case we have other sectors in which higher wavelengths are needed, that's why we also did develop in this third technology, laser technology. How has been our work? Well, we want to go from here, in which we have turbulent flow in the demonstrators, the turbine and the fan, and go to a quasi-laminar flow in which the drag is clearly reduced. For this, as I said, we have had to do some simulations, in this case by surface technology, these simulations. And the first difference is that we had two totally different cases, because for the turbines, we obtained the best wavelets below 550 micron, and for the fans, the wavelets, target wavelets were 100 microns or above. So this is the first difference. The second difference is that the wavelets are going to be inscribed onto the turbines directly, so we will have to inscribe directly the wavelets. In the case of the fans, as they are manufactured by injection molding, we need to engrave the negative of the wavelets in the injection molding. So what has happened in this case, due to the different periods we needed for different demonstrators, despite the initial idea was to integrate only one laser technology, we integrated the second one. It was a contingent measurement we already included in the proposal. So we integrated the DLIP and direct laser writing. For the DLIP, apart of defining the parameters, Fusion Bionic created a module which has a cylindrical lens to be able to cover more area in one pass, and also that it was robust in a set direction to avoid any, or to be more robust due to the changes in the distance from the focal plane. We did some tests. They already did the module, and the result was very positive and very robust in set direction. Okay. In the case of the laser writing, as it was the second technology we needed to include, we were using a scanner and a lens, and we focused here in reducing the processing time as much as possible, changing some parameters as the catch angle, the number of layers. We also work in the burst mode, and we were able to reduce the processing time. Bear in mind that this was for the fans, and as we only need to process the mold once, and then obtain all the replicates. In this case, the time wasn't so central, so critical. So this is the schematic of the final prototype, in which we have the laser source, the optical pads, the two laser modules, and we have to duplicate the monitoring modules that were developed by Aymen. So the monitoring module is an acoustic system in which each microphone receives the sound at different times, and calculating the difference in the time of flight, we can locate the sound of origin and therefore the focal plane. So they did some tests, it worked good, so it was already designed and finished. This is the final prototype, in which all the optical elements are inside this blue box on top of the optical table, and we have the robot which will direct the part to one module or the other, depending on the technology we want to use. The texturing process is quite complicated because these shapes are complex, are not flat. So we have to do a discretization of each of the parts to make sure to divide it in smaller areas to make sure that the laser is always perpendicular to the laser beam, and then also do a good processing strategy to be able to obtain different wavelet periods without discontinuity. So we are doing the texturing right now of the final demonstrators. We don't have yet results for them, but in this pre-validation we did with simpler parts. These are parts injected with the same material as the industrial fans, and we already saw a reduction of 3% in the drag. So this is very promising. So this is all from my side, and thank you for your attention.
Thank you so much, Mikel. We have missed your camera. We can, at least I can see you. I don't know if the
Sorry.
rest of the people
Sorry
can
for
see you,
that.
but don't
I
worry.
think-
It's fine.
Sorry for that.
It's fine. We
Okay.
have here all of you. There is one question for you from Ian. He says, do you control the roughness of riblets for the drag reduction?
Yes, BST or BA Ionic Surface Technologies, as the designers of the and simulators of the riblets that are experts, insisted us of having a low roughness for the riblets, because if not, you can lose the properties of the riblets. And in the case of the glacier rating, we were very focused on that, because we knew that we could even go fastest in faster to obtain the riblets, but the roughness increased a lot. So that's why we use these different strategies with the burst mode, so on and so on. In the case of the delip, also this was main focus, and we had to adjust the parameters to avoid an increased roughness.
Okay, thank you, Mikel. And Sia also asked if you can give us the white paper that they just show us. White paper? I don't know if maybe the
We still don't have it. We plan to do it at the end of the project. Okay, once we have all the results, so we can include everything. Okay, the lifetime studies I see here, not on the turbines, but we did lifetime studies in the features of the fans. They are quite robust in terms of UV and aging studies. Sorry, not for the turbines. Okay, thank you.
Okay, thank you. Maybe we move forward to the next presentation, and if you have more questions to Mikel, thank you. You can ask him at the end. Okay, now is the turn of the Syntex project. Tobias Stiggy is here with us, and the presentation is called From Control to Function, Real-Time Monitoring in Surface Texturing for Sustainable Manufacturing. So maybe, Tobias, you can continue with your presentation.
Yes, hopefully. Hi, my name is Tobias. I'm from founder for AWS, and I will speak about the Syntex project. I'm jumping in for a colleague of mine, which should have given the presentation. So in the Syntex project, one part was the process monitoring itself, and this is also only the part I will present today. I will speak about two approaches we tested: an optical approach and an approach where we recorded the acoustical emission of the process itself. But first, let me tell you shortly why we did this. So the goal of the project was to texture 3D parts, and with a micro texture with DLIP, as shown in the presentation before that, and lips. And of course, if you are trying to texture 3D parts, you have a deviation of the focus position. So this is something you have to monitor to see if your texture worked and if you have a nice quality, a nice uniform texture at the end. So one approach was to measure the texture after the process itself. And therefore, there are, of course, quite a few possibilities. We tried spectroscopy, so we wanted to see if we can measure the micro texture quality by spectroscope. And of course, there are a few different approaches you can do. You can do it from first sight. What we did in the project is we developed a method where we directly included the spectroscope measurement in the beam path of the micro texturing head itself. So we had a white light source, of course, in the spectrometer, and we used the beam path, and we used the same scanner as well as the same theta lens as the texturing module itself. So you can texture and then directly measure your surface by spectroscopy. So here are some results from spectrometer for direct laser interference patterning, which is the superimposing of two beams as shown in the presentation before for two different influence and of course different overscans to achieve different texture depths. And as you can see, these measurements were done with textures at different working positions, so out of focus and in focus. And you can clearly see there's a difference in the spectrums. So to develop an automatic system which can then say this worked not, we feed this information into machine learning and neural algorithms to try to find an algorithm which can then predict if the texture worked and was done in focus and therefore was a uniform texture. And this worked really good. So first we started, of course, with the full spectrum, and we had accuracies up to 99%. And then we even reduced the information we gave the network, the neural network. So we only used the top 10 features, so the top 10 wavelengths, which were identified by the algorithm, using, of course, a random forest algorithm to do feature importance. And even with this, we achieved accuracies up to 99%. Which means you can do your texturing, and then without moving the piece, you can do a spectroscopy, and then know if this texture was done in focus or out of focus. And even for those algorithms, you can say how far it was out of focus. And this means you can control your process and redo the process or do it with different laser powers. The second approach we tested was to record the acoustical emission of the process itself, so without touching the beam path. Therefore, we used normal microphones, which were located at the structuring head. And here you see, for this approach on the right side, you see a simulation of DLIP. So you have those two beams which are superimposed, and you see this interference where the texturing is happening, so where we generate microtexture. And you also see the focus of the individual beams. On the left side, you see the acoustic response of the process, so the noise, just the noise you can hear. And you see that you have like two regimes. One where it's quite loud, where you have the interference pattern, and then there's one which is not as loud, or the noise is not loud, where we have the focus of the individual beams. Which means such a system can directly use to find the autofocus automatically. With a microphone, see when the process is the loudest, and then you can hear if you are in focus. Of course, this is we wanted to go further in the project. And for example, we have a laser which is a little bit older and changes in laser power a little bit. And therefore, we have textures which have different depths. So if the laser power is reduced, because the laser is old, then you can see in the pattern the texture gets lighter, and of course this means the microtexture is not as deep. So what we did here, we also used the noise of the process itself and feed this to an PE controller to control the input power of the laser and therefore the output power of the laser, of course. Obviously, this acoustic signal is not just the maximum amplitude, it's heavily filtered, as well as there are specific frequency ranges which we looked at. And what you can see here on the left side is the process without this active control of the laser power, and you have like invalidation in the depth, as well as the resulting roughness. And on the right side, you see the same system, nothing changed, so just attached an acoustic module, and we constantly controlled the laser, and we could get the error of the resulting surface under 10%. So we had like a constant or a uniform texture. This so the second step is, of course, when you record your acoustic or the acoustic of the process, you can also do some post-processing, and this is what is shown here. So after recording the whole process, we did like a 2D image of the surface, and as it gets louder, the noise changes, the amplitude of the changes, and this we just 2D plotted for the whole field. And what you can see here that this process, this should of course be like a uniform color, which would mean the process was in a uniform focus position, but this was slightly tilted, and this is something you can calculate afterwards and say the sample was tilted in X and Y direction. And this is of course quite independent of the process speed, as you just record and then do the calculation. So both of those systems were integrated into a machine by LASEA. So we have an optical module which can be attached from the right side to a texturing head. of course, you need the specific entry hole and the mirrors inside. And we developed a monitoring module which can just be used from below and records the acoustic. And both of those systems, the optical as well as the acoustical system, have like an embedded computer where also algorithms run. With this, I will finish my presentation. Just 1 minute overdue. Yes, so I showed you that this works. That is currently running at LASEA as part of the Syntax project, doing the final test for 3D processing. And for both with the spectroscopy as well as the acoustic, you can monitor your process. Thank you. And I'm happy to answer any questions.
Thank you for your presentation. We have a question in the chat. Shia is saying how long it takes to include the ML for decision for in-time monitoring of DL-LEAP and LEAP process.
So for the spectroscopy, of course, you have to do some. So we did a larger data set of texture, and then we trained a machine learning system, which is like trained offline, and then the interference of the network itself, so not the interference of the caching, so the interference of using the network. This, as I showed you, we're only half a second or below half a second with this optimized network.
Okay, thank you, Tobias. We'll have more time for questions in the end. Thank you for your presentation. Now, last but not least, we have our last speaker of the day. His name is Sebastian Slowik, and he will be presenting the project CLASCO. This project studies how laser polishing and laser surface functionalization are used as additive manufacturing post-processing steps that will lead to enhanced biocompatibility, reduce friction in implants, improve corrosion resistance, and friction in aerospace components. Sebastian, the floor is yours whenever you want to share your presentation. Thank you.
Thank you. Can you see my screen?
Yes.
Yeah.
Yes, perfect. So thank you and welcome to the CLASCO project. You all know the current challenging of the European manufacturing industry in point of sustainability, digitalization, and innovation. For example, we have a lot of conventional machining and casting with high energy demand. We have, in some situations, unsustainable materials. We have needs in digital twin, manufacturing quality, and advanced functionalities for application. CLASCO is trying to solve that issue. We are focusing on the additive manufacturing technology. As this technology is a lightweight engineering technology, and we are focusing on the post-processing to achieve functional surfaces in different use case areas. Our use case areas are in aerospace and medical devices. And the big benefit of it is that you use no chemicals. It's a localized treatment. You have no coatings, less energy compared to conventional machining. You achieve advanced functionalities, and the process is digitizable for quality improvement and also self-learning. The idea of CLASCO is that we are doing part fabrication and afterwards post-processing. We have 3 processes. One is the fabrication, additive manufacturing, the laser powder bed fusion. Afterwards, we have the CLASCO process in the CLASCO machine. It's consisting of laser polishing and laser surface texturing. This is the CLASCO machine where this happens. Then we have monitoring of these laser processes with an MWIR sensor and a plasma sensor. The first one is going on the melt pool, the second one on the plasma. And finally, we would like to do self-learning of these laser processes to achieve digital twin and at the end prediction of the process. Moreover, we have 3 different use case companies: Airbus, Dupuis Synthes, and CT, sustainability part, and of course, dissemination, communication, and exploitation. As I said, our 3 processes consists of first the part fabrication. It is selective laser melting or laser powder bed fusion in an inert argon atmosphere. We produce titanium and aluminum alloys there. Afterwards, we have the post-processing. This is happening in the CLASCO machine, which you can see here, basically, the inner part of it from Sila's laser system. There we do first the laser polishing with a reduced oxygen level in an inert chamber, as you can see here. And secondly, we have laser surface texturing. We also use the direct laser interference patterning technology as the previous two projects. We use the ellipsis optical head observed function, which shows a very much enhanced depth of focus, which is very much beneficial for 3D components. Our use cases, first the titanium one. These are used in medical devices. One is the knee implant. This is the femoral component of the knee implant, as you can see here. It's half of a full knee implant. Normally it was a casted, or before it was a casted cobalt chromium alloy. CLASCO would like to replace that by an additive manufactured titanium alloy, which is of course by the material already more sustainable. And yeah, first what we did, we optimized the design of the part. And this is the final use case part. And of course, what you want to achieve there is better functionality in friction and biocompatibility. The second use case is the trauma plate. It's used to be attached on bone to help the bone healing by itself. This is a representative shape. Previously, it has been machined. Now, the project aims to produce it from additive manufacturing. We also designed this part, optimized the design, and finally, we 3D printed these parts. And for example, here is afterwards the treated surface that we treat in the CLASCO project. Afterwards, after manufacturing of the parts, we do the laser polishing. This is shown here. Here you see typical appearances in the additive manufacturing process, like molds and droplets, a high roughness. And this is also the core of the CLASCO project, that we can deal with high roughnesses. After laser polishing, you see a big improvement here, which is also shown in the roughness values, which are considerably reduced. After the laser polishing, we do laser surface texturing. As I said, you can do that with different kinds of lasers. One is picosecond, the other one is nanosecond. In both cases, you can see that you get a wave pattern based on two beam laser interference. And we did a parameter optimization here. And you can see, for example, in this parameter set, we get a quite nice result between picosecond and nanosecond. There are also different functionalities you can achieve. For example, here you can achieve more microstructural or more surface features than here. The nanosecond interference patterning technology is more smoother, so you can achieve different features for different properties. At the end, the CLASCO machine will contain a picosecond laser in that sense. The structure depth is also very high in homogeneity as well. In case of the aluminium, we use apart from the belly fairing of the A350 as a use case alloy, which is an actuator, an actuator bracket, and the nozzle that is built in there, which previously from titanium, now is built based on skalm alloy. Also here with the design optimization and the printing of the part. And the other one is the lever of this nozzle actuator. And of course, the application here, the functionality you want to achieve is friction reduction and also a corrosion resistance. The final use case part is the satellite's separation mechanism from the Ariane rocket, the clamp band, which is shown here. And this also we did design optimization, and in all the components we achieved a weight reduction of more than 25%. And at the end, these are the treated parts. Also here we did laser polishing with a considerable roughness reduction with and without sandblasting. And we also did the laser surface texturing with more or less the same result, but in this case it is more challenging regarding the scalp alloy because the initial roughness is higher and the material is more challenging to process. And finally, I can show you some 3D geometry treatment we did, some preliminary results. For example, this is one of the biomedical use cases. Here you can see the 3D shaped surface, and we did some parameter variations here. And for example, you can see that in parameter set 5, the surface looks the smoothest. So there we achieved a minimal roughness here, because at the end, that's the core of the project, to treat 3D shaped part. And that will continue within the project, which is of course not like some of the other projects, not in its end phase, but in its end of middle phase. And then we also tried the laser surface texturing process on such a component, 3D component. And as you can see here, also visible through this rainbow shining, that we could achieve a well-structured quality also among this curvature here. And thanks to our DLIP optics, which leads to an enhanced depth of focus, we can achieve here a very nice result over a depth of focus of in the millimeter range. Yeah, short summary and outlook. So all use case parts have been additive manufactured and reached quality requirements. Laser polishing reduced the roughness considerably. After laser polishing, the laser surface texturing structured the part surfaces. Picosecond delete gives us more functionality features here. The next steps will be that the completely 3D use case samples will be treated in the machine under inert atmosphere. We will demonstrate the functionality for the final parts, and inline monitoring and the AI process implementation will be further implemented also for prediction. And yeah, we will show that the technology is applicable for all 3D printed parts, of course, after seeing the process limits that are valid. And we want to go from TRL3 to 4 to TRL6 at the end of the project. So demonstration of technology and the business cases we have potentially are the use cases, the CLASCO machine itself, hardware, software, and services. And by that, I would like to thank you for your attention.
Okay, thank you so much, Sebastian. I think there are really promising results from your project. I don't know, to the moment there is no question for you, so I think you have been very clear with the explanation. So if this is not a problem for you, we move on to the next panel discussion. This is more to talk about some of the key challenges in implementing these functional surface technologies across different industries, both from a technical and economic perspective, which is also important. So we'll also look at how collaboration between these projects can open new opportunities and create real cross-sector impact. So let's start with this conversation, and I'd like to invite our experts from the presented project to share their views on this topic. I have a first question for Belén. So from your experience with advanced corrosion-resistant coatings, what do you see as the biggest obstacle for large-scale industrial adoption? Is it the cost of implementation, or maybe the need for standardization, or the market's reluctance to adopt new processes? Which is your opinion? And maybe if the public wants to ask some questions for these experts, please join the debate. It's a free and open debate and discussion. Belén, if you want.
Okay, thank you for the question, Silvia. I would say that the biggest obstacle is more about cost and mindset than the technology itself. because we already know that processes like cataphoresis are widely used, especially in the automotive sector. So the concept is quite well established. And I would also like to say that our anaphoretic coating, the one that we have used in this project, is also a commercial technology, but it is used for less demanding applications. So what we have done is to adapt and optimize it for different alloys, aluminum alloys, and also for other type of requirements. And currently, we are also developing our proprietary formulations that are more environmentally friendly.
That's important.
And I would like to add also that another important point is that this anaphoretic process is quite easy to integrate in existing anodizing lines, because in most cases you only need a final tank with the ultrafiltration system and also an oven for the thermal treatment. So the investment isn't that big. So for me, maybe the real challenge is simply building confidence to the market.
Yeah, for that, this session is perfect, I think, to bring confidence and make things easier to the industry and to the market. No, I think this is a good session for that. So thank you, Belén. The second question will be to Miguel and to Sebastian, because both Vilasurf and CLASCO are applying laser-based surface functionalization, but in very different contexts, aerodynamics and also biomedical and aerospace from CLASCO. So I wanted to ask you, do you see potential for combining these approaches or collaborating across sectors to accelerate the adoption of the industry? Or maybe it's a very difficult thing to do at that point, at least.
Okay, I will start. From my experience, each sector it's very particular, not only in terms of technical requirements, but also in terms of normative environment and so on and so on. So yes, some of the developments you have done thinking about one sector, you can take it to other sectors. In our case, as our main texture is drag reduction, in this project, it would have to do with the reduction in with applications in which the drag reduction is important. Okay, so yes, we can use the laser to texture other shapes, but we had to recombine it or to rethink the technology. So maybe it's not that simple. Specifically, seeing what they have done, not. But yes, of course, we can collaborate between the partners of the project. Yes.
I can add something.
Of course.
Yeah, I think every one of us has its speciality, of course, and we can also learn from each other. The CLASCO project is, for example, more focused on rough surfaces. So if you have parts on more rougher surfaces, we might be able to help you because we have this polishing techniques. On the other side, our chamber in this CLASCO machine is limited in size. So maybe I saw a robot in Vilasurf's project. So with larger parts, maybe this can help you more. In our chamber, if you have issues with oxidation, for example, like with titanium materials, we might be able to help you better. So it, as you said already, it depends on the context and on the application area.
That's interesting. Thank you so much to both of you. Now, regarding the cross-sector opportunities, this question is to Francisco from Fabulous. These metasurfaces are revolutioning optical sensors, he said. So beyond your current industrial applications, do you envision synergies with other functional surfaces technologies presented today, such as, for example, monitoring from Syntex or coatings from Surgicoat?
Yeah, I mean, monitoring is always something which is interesting for the manufacturing side. I mean, having a tool that allows you to fabricate, or not to fabricate, to follow the fabrication of the structure that you are doing your manufacturing is always helpful. And regarding the coatings, sometimes the use of coatings in let's say in cooperation, working in cooperation with the structure that we are fabricating can be of help for the fabrication of metasurfaces for reflective or several other kind of applications. So yes, in a way they could be combined for certain applications, but as Sebastian mentioned, we all have our own knowledge or capabilities, and sometimes combining our capabilities can help us develop new applications or provide new functionalities to the materials that we are fabricating. For example, I'm thinking about not only optics, which is our case, but providing extra functionalities to the optical surfaces, how they react with the environment. This is also important to improve the lifetime of some materials or some applications.
That's interesting point. Thank you, Francisco. And to finish this discussion, I don't know if any one of you have to point out some other topic, but regarding future impact, this one goes to Tobias. Is this real-time monitoring is a game changer for sustainable manufacturing, as you all agree. So how do you see monitoring technologies like Syntex enabling the integration of functional surface innovation across different industries in the next 5, I wouldn't say 10 because it's too far.
Okay.
Years? How do you see it?
Yeah, thank you for this question. I think a lot of those monitoring setups shown today, not only in Syntex, we are kind of independent of the specific process they were tested for. Also spectroscopy I showed also works for lips, for example, and the acoustic sensor works for different laser processes. So I think what we'll maybe see in the future is that there will be a lot more independent sensors, which you can just get from shelves, so just buy it and test for your process. So there will be less highly integrated process monitoring sensors into different processes, into different technologies. So I think this could be a possible thing in the next 5 to 10 years. Like the plasma sensor shown on the project before, after me, which is something you can just buy, attach, and use. And this I can see also for acoustic sensors, spectroscopy sensors, and other sensors which were shown for monitoring.
That's hopefully we see that. Thank you so much, Tobias. For my part, I think that this discussion is quite interesting with your insights. So thank you all. I don't know if from the audience they have more questions to you, but there was one later, from Aidan that goes to Francisco that said that which polymers do you work with in Fabulous, Francisco?
Okay, we are using ormosers. I mean, hybrid polymers, organoceramic and hybrid polymers. That's the material that we mainly use for the fabrication of the metastructures, which are, once they are cured, they have a similar mechanical and optical properties to glass. That's the reason we use them.
Okay, thank you. I don't know if Aidan is still here, but I hope we solved his question. So I don't know. Okay. I don't know if there's any more questions to you or if you want to ask one. Okay, Anne. Hi.
Hello, hi. It's Anne from Fusion Bionic. I have a question to Sebastian regarding the laser process. So did you use shielding glass during the laser process? And did you need to clean the samples afterwards?
Did you clean what? The samples?
The samples, yeah, the samples.
So we used an argon atmosphere in the processing chamber of the CLASCO machine. And afterwards, maybe my colleagues can add something to that, but I don't think that we cleaned the sample in a way. But I mean, at the end, the idea of the project is that we have just these laser processes and no chemicals involved afterwards. So from the industry perspective, yeah, we tried without any post-chemical treatment.
Okay, thank you.
Thank you, Anne. I think you've been really clear with your presentations because there is no questions for you. There's any more? Maybe they are still processing all the information and maybe the questions come later. So I think we'll be really on time. So okay, I think there's a question here. Alexander, he says, how the laser process developers see the acceptance of laser technology by the industry, taking into account sustainability and safety aspects. Which one of you want to answer this question? The laser process developers? Maybe Michael? Or I don't know which one.
Okay. I suppose by safety you mean that there could be added risks due to the laser beam and the impact it can have in the workers that are not familiarized with this technology. There are two things. First one is you have to be careful to assess all the risks that you include when you include a machine or a technology in this type. So doing like a what if or a fault tree analysis to make sure that everything is covered. And another very important thing in this specific technology is the training of the workers, and they insist that you have to insist in the risks it poses. Because as we may all know from industry environments, the most important risk is when somebody thinks that they know enough and they relax. And then is when accidents can happen. So that's my point of view.
Yeah.
Maybe I can add. So I think that laser sources are getting cheaper every year, and I think this has to do more that they will be adopted into the industry. But this also means that laser machines get cheaper, or hopefully get cheaper from larger manufacturers, and those are typically, if used as intended, quite safe. So I think such larger laser machines will be adopted quite easily. So such open systems on optical tables, I think, will not be used in industry. So also for example, for DLIP, they are like you can buy ready machines with everything inside, so that you don't need an optical table to do this. And I think there's and if you train your factory workers quite good, then I think the safety is acceptable.
Thank you. I hope, Alex, we solved your questions. So maybe, okay, you're welcome. I don't know if there's more questions or more comments you want to ask or add to this session. If not, maybe it's time to end this session, this webinar. So thank you all. Maybe if we have more comments or more doubts, you share your emails, I think, but if not, you can write to SECFO and we put you in contact with all the partners. So thank you so much all for joining us today and for sharing this interesting presentation. We're glad to have you here, and let's continue innovating. Thank you all.
Okay, thank you.
Bye.
Bye.
Thank you, everyone.
Bye. Thank you.
Thank you. Bye.
Bye.